Hello, my dear students and the rest of the learners. Welcome to this presentation in which we are going to continue with learning on the topic device input-output management in operating systems. This is part 2 of the 5-part series of presentations in this topic. In this presentation, we are going to look at the principles of input-output software. My name is Meme JM, or you can simply call me Emily Swap. In this presentation, we are going to look at the input-output software layers, the interrupt handlers, device drivers and their installation, device-independent I/O software, user space I/O software. Let's commence by looking or discussing on I/O software layers. The basic and effective idea of I/O software is to organize it as a series of layers of abstraction, with the lower layers concerned with the hiding of peculiarities of the hardware from the upper ones, and the upper ones concerned with presenting a clean, nice, and regular interface to the users. The figure below summarizes the I/O software system, showing all the layers and the principal functions of each layer. Each layer has a well-defined function to perform and a well-defined interface to the adjacent layers. The functionality and interfaces differ from system to system. Therefore, the goals or issues of I/O software can be achieved in an efficient way by structuring I/O software in layers from the bottom as follows. At the lowest layer, we have hardware layer, followed by interrupt handlers, then device drivers, device-independent software, and finally, we have the user processes. These layers can be illustrated or demonstrated as follows. On the upper layer, we have the user-level I/O software, which we also call the user processes layer. It is said to be the upper layer because it is the layer that is close to the user, or it is the layer through which or in which the user interacts with a process while executing a certain task. Below the user level I/O software layer, we have the device-independent OS software layer. It is important to note that the user level I/O software layer executes various functions, with one of the functions being to make I/O requests, to format I/O, and also to perform spooling tasks. The device-independent OS software layer deals with handling, the naming, the protection, blocking, buffering, and allocation functions. And therefore, when the user issues a request through the user-level I/O software, this I/O request is passed over to the device-independent OS software layer. This request is then forwarded or passed over by the device-independent OS software layer to the respective device drivers layer. The device drivers layer is in charge of setting up device registers, as well as checking the status of those registers, and even the status of the respective handlers. The device drivers then passes over the I/O request to the next layer, which is the interrupt handlers layer. The purpose of the interrupt handlers layer is to wake up driver when I/O is completed. And then the interrupt handlers pass over the request to the hardware layer, which performs the I/O operation as requested by the user through the user processes. Once the hardware has received the request, it then gives back a I/O reply. And therefore, the hardware layer gives back feedback to the interrupt handlers, which then forward it to device drivers. Then the device drivers forward them to the device independent OS software layer. And then finally, the request or the reply is then issued over to the user process, through which the user is able to know what has happened. And therefore, those are what we call the layers in relation to I/O requests and I/O replies. Let's now focus more on the interrupt handlers. A computer must have a way of detecting the arrival of any type of input. There are two ways that this can happen, known as pulling or polling and interrupts. Both of these techniques allow the processor to deal with events that can happen at any time and that are not currently running. Interrupts are an unpleasant fact of life. Although they cannot be avoided, they should be hidden away from the eye as little of the operating system as possible knows about them. The best way to hide them is to have the driver starting an I/O operation block until the I/O has completed and the interrupt occurs. When the interrupt happens, the interrupt procedure does whatever that it has to do in order to handle the interrupt. Then it can unblock the driver that started it. The net effect of the interrupt will be that a driver that was previously blocked will now be able to run. This model works best if drivers are structured as kernel processes with their own states, stacks, and the program counters. An interrupt handler, also known as an interrupt service routine or ISR, is therefore a piece of software or callback function in an operating system, or more specifically in a device driver whose execution is triggered by the reception of an interrupt. When the interrupt happens, the interrupt procedure does whatever that it has to do in order to handle the interrupt, updates data structures, and wakes up process that was waiting for an interrupt to happen. The CPU hardware has a wire that is called the interrupt request line that the CPU senses after executing every instruction. When the CPU detects that a device controller has asserted a signal on the interrupt request line or bus, when it needs CPU's attention, the CPU saves a small amount of the current state, such as the current value of the instruction pointer, and invokes or jumps to the appropriate interrupt handler routine at a fixed address in memory using the interrupt vector that addresses or whose addresses of OS routines are used to handle various elements. The interrupt handler determines the cause of the interrupt, performs the necessary processing, and executes a return from interrupt instruction to return the CPU to the execution state prior to the interrupt. Therefore, when the interrupting device has been dealt with, the CPU continues with its original task as if it had never been interrupted. The following is a series of steps that must be performed in software by the interrupt handler after the hardware interrupt has completed. Number 1, save any registers, including the PSW, that have not already been saved by the interrupt hardware. Number 2 is set up a context for the interrupt service procedure. Doing this may involve setting up the TLB, MMU, and a page table. Number 3 is set up a stack for the interrupt service procedure. Number 4 is acknowledge the interrupt controller. If there is no centralized interrupt controller, re-enable the interrupts. Number 5 is copy the registers from where they were saved, possibly some stack to the process table. Number 6, run the interrupt service procedure. It will extract information from the interrupting device or devices, controllers, registers. Number 7 is choose which process to run next. If the interrupt has caused some high priority process that was blocked to become ready, it may be chosen to run now. Number 8, set up the MMU context for the process to run next. Some TLB set or some TLB set up may also be needed. Number 9 is load the new process's registers, including its PSW. Number 10 is start running the new process. My dear students and the rest of the learners, I believe that you remember what the acronyms TLB, MMU, PSW, and other terms that I am using in this presentation whenever I am talking about a process, because I discussed in depth these terminologies under the topic on process management in operating systems. If you don't remember what these terminologies or acronyms stand for, I kindly advise that you visit the YouTube channel by the name MLSwap ICT and go through the videos on process management, and by so doing, you will be able to have a clear understanding about these acronyms. However, for now, it is good to remember, or let me remind you, that MMU stands for Memory Management Unit. As can be seen, interrupt processing is far from trivial. It also takes a considerable number of CPU instructions, especially on machines in which virtual memory is present and page tables have to be set up, or the state of the memory management unit is stored, e.g., the R and M bits. The purpose of these bits, the R and M bits, can also be understood in depth from the process management topic. On some machines, the TLB and CPU cache may also have to be managed when switching between user and the kernel modes, which takes additional machine cycles. The interrupt mechanism accepts an address A number that selects a specific interrupt handling routine or function from a small set. In most architectures, this address is an offset that is stored in a table which is called the interrupt vector table. This vector contains the memory addresses of specialized interrupt handlers. Let's now focus on device drivers. A device driver or a device handler is a program which controls a particular type of device that is attached to a computer. It is a device-specific code for controlling a device that is generally written by the device's manufacturer and delivered along with the device on a storage medium or even downloaded from the internet, and especially from the manufacturer's website. These drivers are then installed into the computer, after which they become part of the kernel. The drivers are effectively the interface between the device and the operating system. Device drivers regulate or control computer hardware, and therefore downloading and installing the latest device drivers frequently resolved a number of hardware problems, and especially those which emanate after the device's drivers had already been previously released. Device drivers are often specific to a particular release of an operating system. Many device drivers are built into the operating system, but if you buy a device which was produced after the operating system was released, you may have to explicitly install a device driver which converts the general input-output instructions of the operating system to messages that the device type can understand. Device drivers are not held in ROM like the BIOS, but are loaded into RAM from disk every time the computer starts up. Once a device driver has been loaded, the kernel can call upon the device driver processes to deal with any interrupt from the device, and the I/O system can use device driver processes to control it. Operating system takes help from device drivers to handle all I/O devices. Device drivers encapsulate device-dependent code and implement a standard interface in such a way that the code contains device-specific register, reads, and overrides. The device driver usually provides the required interrupt handling necessary for the time-dependent hardware interfacing. All the device-dependent code goes in the device drivers. Each device driver handles one device type or at most one class of related devices. Device drivers issue commands to the device's controllers, registers, and check that they are carried out properly. The work of a device driver is therefore to accept abstract requests from the device-independent software above it and ensure that the request is executed. The device driver must determine what controller operations are required and in what sequence. The device driver then issues the commands. In most cases, it blocks until an interrupt comes to unblock it. In other cases, it doesn't have to block. Once the operation has been completed, it checks for errors. If everything is okay, it might have some data to pass to the device-independent software. If there are some requests, it processes them. Otherwise, it blocks waiting for the next request. Operating systems usually classify device drivers as block or character device drivers. Most operating systems define a standard interface that all block drivers must support and a second standard interface that all character drivers must support. These interfaces consist of a number of procedures that the rest of the operating system can call to get the driver to do work for it. A driver typically communicates with the device through the computer bus or communications subsystem to which the hardware connects. When a calling program invokes a routine in the driver issues commands to the device. Once the device sends data back to the driver may invoke routines in the original calling program. Drivers are hardware dependent and operating system specific. They usually provide the interrupt handling that is required for any necessary asynchronous time-dependent hardware interface. Since each operating system needs its own drivers, device manufacturers commonly supply drivers for several popular operating systems. Since the designers of every operating system know that pieces of code or drivers written by outsiders will be installed in it, it needs to have an architecture that allows for such installation. This means having a well-defined model of what a driver does and how it interacts with the rest of the operating system. Device drivers are normally positioned below the rest of the operating system as illustrated in the following diagram. As you can see from this diagram, on the upper part, we have what we call the user space. And in this user space, we have user programs that the person or the user interacts with. Then through the user process, the requests or communication is done, and this request is passed over to the kernel space. This kernel space is composed of the rest of the operating system as well as the various drivers. For example, from this diagram, we have printer driver that communicates with the printer controller, which is in charge of communicating with the printer device. We have camcorder driver, which communicates with the camcorder controller that is in charge of the camcorder. We have the CD-ROM driver that communicates with the CD-ROM controller in order to be able to handle the CD driver or CD drive. And therefore, on the upper part, we have the user space, which is followed by the kernel space, where we find the various drivers. And then we have the hardware, and at the lower level, we have the devices themselves. A device driver has several functions. These include, number one, to accept abstract read and write requests from the device-independent software above it and see that they are carried out. Number two is initializing the device if needed. Number three is managing its power requirements and log events. Many device drivers have a similar general structure. A typical driver starts out by checking the input parameters to see if they are valid. If they are not, an error is returned. If they are valid, a translation from abstract to concrete terms may be needed. Next, the driver may check if the device is currently in use. If it is, the request will be queued for later processing. If the device is idle, the hardware status will be examined to see if the request can be handled now. It may be necessary to switch the device on or start a motor before transfers can begin. Once the device is on and ready to go, the actual control can begin. Controlling the device means issuing a sequence of commands to it. The driver is the place where the command sequence is determined depending on what has to be done. After the driver knows which commands it is going to issue, it starts writing them into the controller's device registers. After writing each command to the controller, it may be necessary to check to see if the controller accepted the command and is prepared to accept the next one. This sequence continues until all the commands have been issued. Drivers are not allowed to make system calls, but they often need to interact with the rest of the kernel. Usually, calls to certain kernel procedures are permitted. Drivers have to be reentrant, meaning that a running driver has to expect that it will be called a second time before the first call has completed. In a hot pluggable system, devices can be added or removed while the computer is running. As a result, while a driver is busy reading from some device, the system may inform it that the user has suddenly removed that device from the system. Not only must the current I/O transfer be aborted without damaging any kernel data structures, but any pending requests for the now vanished device must also be gracefully removed from the system and their callers given the bad news. Furthermore, the unexpected addition of new devices may cause the kernel to juggle resources. For example, interrupt request lines, taking old ones away from the driver and giving it new ones in their place. Drivers are not allowed to make system calls, but they often need to interact with the rest of the kernel. Usually, calls to certain kernel procedures are permitted. Device I/O driver installation. The process of installing a device driver is almost similar to that of installing other computer programs. This is because a device driver is also a software, but one that makes a device to become operational. Installation or setup of a computer program is therefore the act of making the program to be ready for execution. Because the process varies for each program and each computer, programs often come with an installer, which is a specialized program that is responsible for doing whatever that is needed for their installation. Installation typically involves code being copied or generated from the installation files to new files on the local computer for easier access by the operating system. The following are the various types of software installation. Number one, we have what we call the attended installation. This is an installation process which usually means a user who attends to it in order to make choices during the installation process. Number two is what we call silent installation. Installation, or this is an installation that does not display messages or windows during its progress. Number 3 is unattended installation. Installation that is performed without user interaction during its progress or with no user present at all. That is, an attended installation is an installation which is performed without user interaction during its progress or with no user present at all. Number 4 is headless installation. This is an installation which is performed without using a computer monitor connected. Another machine connects to the target machine, for instance, via a local area network, and takes over the display output. Number 5 is scheduled or automated installation. This is an installation process that turns or runs on a preset time or when a predefined condition transpires. Number 6 is clean installation. A clean installation is one that is done in the absence of any interfering element, such as old versions of the computer program being installed or leftovers from a previous installation. Number 8 is network installation. Or number 7 is network installation. Network installation, or shortened net install, is an installation of a program from a shared network resource that may be done by installing a minimal system before proceeding to download further packages over the network. The following are the main steps that are involved in installing software inclusive of drivers. Number 1, you should start by reading the manuals for the device provided for by the manufacturer. Number 2, verify that the target system meets the general hardware requirements of the application. Number 3, make sure that the version of the drivers you are installing corresponds to the operating system platform which is running on your machine. Number 4, double check if you need to update or upgrade your drivers, or if there is a need to download other tools or utilities. Number 5, once all the initial requirements have been met, make sure that there are no unnecessary programs running before beginning the installation procedure. Number 6, software installation can be done either from the internet, that is skip to number 8, or from an installation disk, which is provided for by the software manufacturer. In order to install your drivers from the disk, you need to simply insert the driver's disk into its drive. Then you open the CD or DVD and run open the installer file or the setup file. Number 7, once you have clicked on the installer file, or if the device, for example, the CD, runs automatically, a setup wizard window will be launched. In case there is none, you should open the Explorer and navigate to the optical drive. Then you double click on either the autorun or setup file. Number 8, once the wizard is running, simply follow the prompts until the installation process is completed. Number 9, for installation from the web, launch your browser application and download the setup file to your hard drive. Number 10, after completion of the downloading process, run the setup program to execute the setup wizard that will handle the automatic installation of the software for the device. Then, after the installation procedure has been completed, it is necessary that you reboot your machine in case the operating system prompts for the action. And even if the operating system does not prompt for the reboot action, it is always advisable that after you make your installation, you reboot your machine. Let's now look at device-independent I/O software. Although some of the I/O software is device-specific, other parts of it are device-independent. The exact boundary between the drivers and the device-independent software is system and device-dependent because some functions that could be done in a device-independent way may actually be done in the drivers for efficiency or other reasons. The basic function of the device-independent software is to perform the I/O functions that are common to all devices and to provide a uniform interface to the user-level software. Though it is difficult to write completely device-independent software, we can write some modules which are common among all the devices. A major issue in operating system is normally how files and I/O devices are named. The device-independent software takes care of mapping symbolic device names to the proper drivers. Closely related to naming is protection. Different disks may have different sector sizes. It is therefore up to the device-independent software to hide this fact and provide a uniform block size to upper layers, for example, treating several sectors. Also, some device drivers or some devices deliver their data 1 byte at a time, for example, the modems, while others deliver theirs as a block, for example, the NIC or network interface card. These differences must be hidden. Buffering is also an issue for some or for both character and block devices. When a file is created and filled with data, the new disk blocks have to be allocated to the file. To perform this, the operating system needs a list or bitmap of free blocks per disk, but the allocation algorithm is device independent and can be done above the level of the driver. Some devices can only be used by one process at a time. It is therefore up to the operating system to examine requests and for device usage and accept or reject them depending on whether the device is available or not. The device driver does error handling. The driver reports the error to the system-dependent software, then how it is treated from there on is device independent. Therefore, the following is a list of the functions of device independent I/O software. Number one is what we call uniform interfacing for device drivers. A major issue in an operating system is how to make all I/O devices and drivers look more or less the same. If disks, printers, monitors, keyboards, amongst others, are all interfaced in different ways, every time a new peripheral device comes along, the operating system must be modified for the new device. Having to hack on the operating system for each new device is not a good idea. One aspect of this issue is therefore the interface between the device drivers and the operating system and the rest of the operating system. If each device driver has a different interface to the operating system, it would mean that the driver functions available for the system to call differ from driver to driver. It might also mean that the kernel functions that the driver needs also differ from driver to driver. Taken together, it means that interfacing each new driver requires a lot of new programming effort. Therefore, with a standard interface, it is much easier to plug in a new driver, provided that it conforms to the driver interface. In practice, not all devices are absolutely identical, but usually there are only a small number of device types, and even these are generally almost the same. The way this works is as follows. For each class of devices, the operating system defines a set of functions that the driver must supply. Often, the driver contains a table with the pointers into itself for these functions. When the driver is loaded, the operating system records the address of this table of function pointers. So when it needs to call one of the functions, it can make an indirect call via this table. This table of function pointers defines the interface between the driver and the rest of the operating system. All devices of a given class must obey it. Number 2 is device naming. Another aspect of having a uniform interface is how I/O devices are named. The device-independent software takes care of mapping symbolic or mnemonic device names onto the proper driver. All devices have major and minor numbers, and all drivers are accessed by using the major device number to select the driver. Therefore, in uniform naming of devices, the name of a file or device should simply be a string of characters or an integer not dependent on the device in any way. In this way, all the files and devices are addressed in the same way, that is, by their path name. Number 3 is device protection. Closely related to naming is protection. It is a method or a way through which the operating system prevents users from accessing devices that they are not entitled to access. So, to deal with this, in various operating systems, devices appear in the file system as named objects, which means that the usual protection rules for files also apply to I/O devices. The system administrator can then set the proper permissions for each device. Number 4 is providing a device-independent block size. Not all disks have the same sector size. It is up to the device-independent software to hide this fact and provide a uniform block size to higher layers, for example, by treating several sectors as a single logical block. In this way, the higher layers only deal with the abstract devices that all use the same logical block size independent of the physical sector size. Similarly, some character devices deliver their data 1 byte at a time, for example, modems, while others deliver theirs in larger units, for example, network interfaces. These differences may also be hidden. Number 5 is buffering. To avoid overheads and inefficiencies during processing of input or output, it is sometimes convenient to perform input transfers in advance of requests being made and to perform output transfers sometime after the request is made. This technique is known as buffering. Buffering is a technique that smooths out peaks in I/O demand. However, no amount of buffering will allow an I/O device to keep pace with a process indefinitely when the average demand of the process is greater than the I/O device that it can service. Even with multiple buffers, all of the buffers will eventually fill up and the process will have to wait after processing each chunk of data. However, in a multi-programming environment, when there is a variety of I/O activity and a variety of process activity to service, buffering is one tool that can increase the efficiency of the OS and the performance of individual processes. The following are some of the buffering schemes or approaches that are supported by operating systems to improve the performance of the system. Number one is single buffering scheme. This is the simplest type of support that the operating system can provide to a user for issues an I/O request. The operating system assigns a buffer in the system portion of main memory to the operation. In block-oriented devices, this scheme works as follows. Input transfers are made to the system buffer. When the transfer is complete, the process moves the block into user space and immediately requests for another block. This is called reading ahead or anticipated input. It is done in the expectation that the block will eventually be needed. For many types of computation, this is a reasonable assumption most of the time because data are usually accessed sequentially. Only at the end of a sequence of processing will a block be read in unnecessarily. This approach will generally provide a speed up compared to the lack of system buffering. The user process can be processing one block of data while the next block is being read in. The operating system is able to swap the process out because the input operation is taking place in system memory rather than user process memory. This technique does, however, complicate the logic in the operating system. The operating system must keep track of the assignment of system buffers to user processes. The swapping logic is also affected. If the I/O operation involves the same disk that is used for swapping, it hardly makes sense to queue disk writes to the same device for swapping the process out. This attempt to swap the process and release memory or release main memory will itself not begin until after the I/O operation finishes, at which time swapping the process to disk may no longer be appropriate. Similar considerations apply to block-oriented output. When data are being transmitted to a device, they are first copied from the user space into the system buffer from which they will ultimately be written. The requesting process is now free to continue or to be swapped as necessary. Number two is double buffering or buffer swapping. This is an improvement of a single buffering, which is implemented by assigning two system buffers to the operation. A process now transfers data to or from one buffer while the operating system empties or fills the other. In order to ensure that slow device still has somewhere to write data while previous data is being transferred into memory. A second buffer is used, and the two buffers alternate as each becomes full. This is known as double buffering. Double buffering is often used in animated graphics so that one screen image can be generated in a buffer while the other completed buffer is displayed on the screen. This prevents the user from ever seeing any half-finished screen images. With this buffering scheme, it is possible to keep the block-oriented device going at full speed because it ensures that the process will not have to wait on an I/O. However, this involvement or this improvement comes at the cost of increased complexity. Also, for stream-oriented input, we are faced with the two alternative modes of operation. For line-at-a-time I/O, the user process needs to be suspended for input or output unless the process runs ahead of the double buffers. For a byte-at-a-time operation, the double buffer offers no particular advantage over a single buffer of twice the length. In some cases, the producer-consumer model is followed. A double buffer scheme should smooth out the flow of data between an I/O device and a process. If the performance of a particular process is the focus of our concern, then we would like for the I/O operation to be able to keep up with the process. Double buffering may be inadequate if the process buffers I/O. In this case, the problem can often be alleviated buffers. Number 3 is circular buffering. When more than two buffers are used, the collection of buffers is itself referred to as circular buffer, with each individual buffer being one unit in the circular buffer. This is simply the bounded buffer producer-consumer model that we studied under process management topic, whose videos are already posted in the MLSwap ICT YouTube channel. These I/O buffering schemes can be illustrated as follows. So in diagram A, we have no buffering. In diagram B, we have single buffering. In diagram C, we have double buffering. And the last diagram, diagram D, illustrates what we call the circular buffering. One important aspect or characteristic that you should be able to see, my dear students and the rest of the learners, is that the buffering or a buffer is normally found in between the I/O device and the user process, as is our case in these diagrams. Buffering of I/O is performed for at least 3 major reasons. The first reason is that there are normally speed differences between two devices. So, a slow device may write data into a buffer, and when the buffer is full, the entire buffer or buffer is sent to the first device all at once. Number 2 is the data transfer size differences. Buffers are used in particular in networking systems to break messages up into smaller packets for transfer and then for reassembly at the receiving side. Number 3 is to support copy semantics. For example, when an application makes a request for a disk write, the data is copied from the user's memory area into a kernel buffer. Now, the application can change their copy of the data, but the data which eventually gets written out to disk is the version of the data at the time when the write request was made. Number 6 is allocation and releasing of dedicated devices. Some devices, such as CD-ROM recorders, can be used only by a single process at any given moment. It is therefore up to the operating system to examine requests for device usage and accept or reject them depending on whether the requested device is available or not. A simple way to handle these requests is to require processes to perform opens on the special files for devices directly. If the device is unavailable, the open fails. Closing such a dedicated device then releases it. An alternative approach is to have special mechanisms for requesting and releasing dedicated devices. An attempt to acquire a device that is not available blocks the caller instead of failing. Blocked processes are put on a queue. Sooner or later, the requested device becomes available and the first process on the queue is allowed to acquire it and continue with execution. Number 7 is error reporting. Errors are far more common in the context of I/O than in any other context. When errors occur, the operating system must handle them as best as it can. Many errors are device specific and must be handled by the appropriate driver, but the framework for error handling is device independent. Errors should be handled as close to the hardware as possible. If the error or if the controller discovers a read error, it should try to correct the error if it can. If it can't, then the device driver should handle it, perhaps by trying to read the block again. Most errors are transient, and if the operation is repeated, they normally go away. Only if the lower layers are not able to deal with the problem should the upper layers be told about it. In many cases, error recovery can be done transparently at a low level without the upper levels even knowing about that error. The following are some classes or types of I/O errors. Number 1 is what we call programming errors. These occur when a process asks for something impossible, such as writing to an input device, such as the keyboard, the mouse, the scanner, amongst others, or reading from an output device, such as printer, plotter, etc. The action taken is to report back this error to the caller. Other errors include providing an invalid buffer address or other parameter and specifying an invalid device. For example, disk 3 when the system has only 2 disks. The action to take on these errors is to just report back an error code to the caller. The other type of errors are called the actual I/O errors. For example, trying to write a disk block that has been damaged, or trying to read from a camcorder that has been switched off. In these circumstances, it is up to the driver to determine what to do. If the driver does not know what to do, it may pass the problem back up to device-independent software. What this software does depends on the environment and the nature of the error. If it is a simple read error and there is an interactive user available, it may display a dialog box asking the user what to do or telling the user what to do. The options may include retrying a certain number of times, ignoring the error, or killing the calling process. If there is no user available, probably the only real option could be to have the system call fail within an error code. However, some errors cannot be handled this way. For example, a critical data structure such as the root directory or free block list may have been destroyed. In this case, the system may have to display an error message and then terminate. There are several aspects to error handling, including detection, correction if possible, and reporting. Number one, detection should be done as close to where the error occurred as possible before more damage is done. This is called fault containment, and this is not trivial. Number two, correction is sometimes easy. For example, the ECC, that is error correcting code memory, does this automatically. But the operating system wants to know about the error so that it can schedule replacement of the faulty chips before unrecoverable double errors occur. Other easy cases include successful retries for failed Ethernet transmissions. In this example, while logging is appropriate, it is quite reasonable for no action to be taken. Number three is error reporting tends to be helpful. The trouble is that the error occurs at a low level, but by the time it is reported, the context is lost. Unix and Linux in particular is horrible in this area. The following are therefore the main goals of I/O software. These are: number one, device independence. Number two, uniform naming. Number three is error handling. Number four is performing synchronous and asynchronous transfers. While number five is handling shared and dedicated devices, while number six is buffering. Let's now look at user space I/O software. These are libraries which provide richer and simplified interface to access the functionality of the kernel or ultimately interactive with the device drivers. Most of the user-level I/O software consists of library procedures with some exception like Spooling System, which is a way of dealing with dedicated I/O devices in a multi-programming system. I/O libraries, e.g., or for example, Studio, are in user space to provide an interface to the OS resident device independent I/O software or SW. For example, putcar, getcar, printf, and scanf are examples of user-level I/O library Studio available in C programming. Although most of the I/O software is within the operating system. A small portion of it consists of libraries linked together with user programs and other programs running outside the kernel. The system calls, including the I/O system calls outside or are normally made by library procedures. The system calls, including the I/O system calls, are normally made by library procedures. Not all user-level I/O software consists of library procedures. Another important category is the spooling system. Spooling is a way of dealing with dedicated I/O devices in a multi-programming system. Consider a typical spooled device, a printer. Although it would be technically simple to let any user process open the character special file for the printer, and suppose a process opened it and then did nothing for hours. In such a case, no other process could print anything. Instead, what is done is to create a special process called a daemon and a special directory called a spooling directory. To print a file, a process first generates the entire file to be printed and puts it in the spooling directory. It is up to the daemon, which is the only process having permission to use the printer's special file to print the files in the directory. By protecting the special file against direct use by users, the problem of having someone keeping it open unnecessarily long is eliminated. Spooling is used not only for printers, but also in various other situations. For example, electronic mail usually uses a daemon. When a message is submitted, it is put in a mail spool directory. Later on, the mail daemon tries to send it. At any given instant of time, a particular destination may be temporarily unreachable, so the daemon leaves the message in the spool with the status information indicating that it should be tried again in a while. The daemon may also send a message back to the sender saying that delivery is delayed, or after a delay of hours or days, saying that the message cannot be delivered. All of this is outside the operating system. Spooling is also used in the network by a network daemon. To send a file somewhere, a user puts it in a network spooling directory. Later on, the network daemon takes it out and transmits it. We have come to the end of this part, that is part 2 in this series of device I/O input-output management, that is device input-output management in operating systems. You can proceed and listen to part 3 of the 5-part series in which I have discussed and explained in depth about disks and disks operations. Congratulations for viewing and listening to this video on the principles of I/O software, which is part 2 of part 5 in device I/O management topic. You can listen to the other parts of device I/O management topic, as well as other videos in the field of computers or ICT from MLSwap ICT YouTube channel. In addition, you can access free life skills, motivational, and inspirational resources from MLSwap Motivation YouTube channel. You can tap on subscribe button for each of these 2 channels for ease of access to the channel's content, and so that you can also receive an immediate update once a new video is uploaded. For any further correspondence, kindly write to us through the email emilyswap@gmail.com. Thank you very much for listening to me, and be blessed.